Welcome back to the wonderful world of physics. This is chapter 20, section 5, matter in electric fields. I want to start by considering how a charged particle behaves in an electric field. You know that the force that a particle feels is equal to its charge times the electric field that it's in. You also know from Newtonian mechanics that the force exerted on an object is its mass times its acceleration. So let's put these two together. We'll say QE equals ma. The force equals the force, so QE equals ma. Solving for acceleration, we get acceleration is Q over m times the electric field. And the sign on the charge, whether positive or negative, will determine its direction. So let's think about what this equation means. How much it accelerates is equal to, in the numerator, its charge. So the more charge it has, the more its acceleration, because it's affected more. But that's going to be counteracted by its mass in the denominator. Mass is an object's resistance to force, and so that will serve to decrease the acceleration. Let's consider a uniform electric field. And I do that just because the math is easier than for a varying electric field. So here we have a parallel plate capacitor setup. We have the positive plate on the top and the negative plate on the bottom so that it's a uniform electric field with the field lines pointing straight down. And we send a charge, we shoot it through from the left, we shoot it horizontally through, and you see that it curves upward. So we can assess what is the sign of the charge. Is it positive or is it negative? And you can see that it accelerated in the direction that electric field lines do not go. Remember that electric field lines always go in the direction that a positive charge would go. So this charge here must be negative. This is the got it question in section 25. It says an electron, a proton, a deuteron, which is a neutron combined with a proton, a helium-3 nucleus, which has 2 protons and 1 neutron, a helium-4 nucleus, which is 2 protons and 2 neutrons, a carbon-13 nucleus, which is 6 protons, 7 neutrons, and an oxygen-16 nucleus, 8 protons and 8 neutrons, all find themselves in the same electric field. Rank in order their accelerations from lowest to highest, under the approximately correct assumption that the neutron and proton have the same mass and that the mass of a composite particle is the sum of the masses of its constituent neutrons and protons. Note any that have the same acceleration. Okay, so we're going to see what their accelerations are, how they compare to each other. Now remember that acceleration is qm over e for a charged particle that's in an electric field. And therefore, acceleration is charge divided by mass. Now, all these particles are in the same electric field. And so it doesn't matter what the electric field is, we're just comparing them given the same electric field. So we can just compare their charges over their m's. The one that has the highest charge per mass is going to accelerate the most. And the one that has the least charge per mass is going to accelerate the least. So I've listed them all out here. It's notable that the mass of an electron is about 1 over 1840 times the mass of a proton, roughly equivalent. And as it suggests in the book, we're just going to assume that the mass of a proton, the mass of a neutron are about the same. And for purposes of this problem, that's an okay assumption to make. So we're going to do the charge per mass of each one. So for an electron, we have its charge, which is E over the mass of an electron, and we get E over 1 over 1840 times the mass of a proton. A proton is E over the mass of a proton. A deuteron, which is a proton and a neutron, is E over twice the mass of a proton. A helium-3 nucleus, well, the nucleus has 2 protons in it. That means it has a charge of 2e for the 2 protons. But it has a mass of 3 nucleons, or 3 protons. So we have 2e over 3mp. The helium-4 nucleus, we consider the charge in the numerator. Well, having 2 protons, it's got a charge of 2e. And having 4 nucleons in it, 2 protons and 2 neutrons, it has, in the denominator, 4 times the mass of a proton. Carbon-13 nucleus, it has 6 protons, so in its nucleus, it's got a charge of 6e, divided by the 13 nucleons, so divided by 13 times the mass of a proton. And finally, the oxygen-16 nucleus has 8 protons in it, so 8e divided by 16 nucleons, 16 mass P. So when I simplify each of these, you can see in the second column that I've just added, the electron is 1840 E over MP. The proton is E over MP. We have 1/2 E over MP. All of these are in proportion to E over MP. 2/3, 1/2, 6/13, and 1/2. And then we just go ahead and rank those in order. So we can see that the lowest one, as the book says to rank them in order from lowest to highest acceleration. So the lowest one of those numbers is 6/13. That's the carbon-13 nucleus. Then there's a tie for the number 2 lowest, 1/2, 1/2, and 1/2. So the deuteron, the helium-4, and the oxygen-16. And then the number 3 lowest is the helium-3 nucleus with 2/3. And then the highest accelerating, the fastest one, is the electron, 1840 E over MP. In an earlier section in this chapter, you got an introduction to electric dipoles, and now we're going to look at how dipoles behave in electric fields. So here's a dipole. You've got a plus on one side and negative on the other side. The dipole moment is, remember, that is P equals QD, so it's the charge. And by charge, the entire charge is 0, but what I mean by charge is the positive side has a charge of plus Q. The negative side has a charge of negative Q. Together, they do add up to be 0, but this is the Q on each side. The dipole moment vector points from the negative to the positive, as you can see in my picture right here. Now, and D is the distance between the positive and negative charge. So you look at the picture, you see this dipole is in an electric field, and the positive side up top wants to go in the direction of the electric field. So it wants to turn to the right. The negative side down at the bottom, it wants to turn to the left, going against the electric field. So the dipole experiences a torque, but no net force, so it's just going to spin around. It experiences no net force because, remember, the total charge on this thing is 0, so it's not going to be accelerated along in the electric field. Rather, the plus side goes one way, the negative goes the other, and we get a rotation. The torque from the electric field will align it with the electric field. So you go from my picture that's at the top that shows the force on the positive side, the force on the negative side, and before long, this is what it's inclined to do. It's inclined to turn so that the dipole moment vector, P, goes along with the electric field. Now let's quantify, let's think about the torque on this thing. Remember from last semester that torque is the cross product of a lever arm times the force applied. And so as a magnitude, we can say that torque on a rotating object is lever arm times force times sine theta. So let's think about the torque on this rotating object, on this dipole. And let's first think about the torque from that positive force about the center. So if you look up at the picture, the force on the positive side, and let's think about what the torque is. Well, that is the distance, the lever arm, I should say, times the force times sine theta. Now the lever arm is half of d because it's being rotated about the center, and the lever arm from last semester, you learned that it's the distance from the axis of rotation to where the force is being applied. So that's going to be half of the length of the dipole, so half of d. The force on that charge is QE, and then times sine theta, whatever the angle is between those two vectors. Now let's go down to the torque on the negative charge. Well, just the same, it's exactly the same. So it's operating with a lever arm of half of d, and it's a charge of QE. We're just taking the magnitude here, ignoring that it's negative. So it's going to be the same and in the same direction, meaning they're both pulling, as my picture is drawn, in the clockwise direction. So they're adding together. So that means that the sum of the torques, the torque on the positive side and the torque on the negative side, they add together, and you get QD times E sine theta. But remember what QD is. I've underlined it there in purple. QD is the dipole moment. And so what we get is that as a vector, the torque on an electric dipole is the cross product of the dipole moment times the electric field. And just a review of geometry of doing vector multiplication. If you draw these pictures, so here I have the vector P oriented as my original picture was, and the electric field, and you use the right-hand rule and see that your thumb of your right hand points into the page, so the torque is into the page. And there's that line above at the top that I had on the previous page. And now as an example, let's say that a dipole is perpendicular to the electric field. So instead of the drawing that you have on the picture there, let's imagine that's a 90-degree angle and the dipole moment is pointing straight up. What is the work that you have to do to rotate it to some angle alpha? Now, this isn't the work that the electric field does. This is the work that some external force comes in and it's going to rotate it from perpendicular to some angle alpha. Well, we learned last semester when thinking about a rotating object where we do work by applying a torque, that work is equal to the integral of torque times d theta. And we take the limits of integration from the initial angle to the final angle. So initially it's pi over 2. You go back to my picture at the top and you imagine that's a 90-degree, a pi over 2 angle, perpendicular. That's the initial. And then we're rotating it to some angle alpha. We go through the calculus here. We're going to say that tau d theta, well, tau as a magnitude is PE sine theta. That's what I have at the top of the page here. D theta. And taking that integral, we're going to take PE and factor it to the outside of the integral. And we're left taking the integral of sine theta d theta, and that is negative cosine theta. And again, limits of integration from pi over 2 to alpha. So coming down here, we have PE times negative of cosine alpha, whatever that is, minus negative of cosine pi over 2. Now, cosine of pi over 2 is 0, so that part just goes away. And we're left with PE times negative cosine alpha, or we can say the work that you do to rotate this dipole, assuming that it starts from a perpendicular angle, is negative PE times the cosine of the alpha you're going to. Now, this looks just like the scalar product. Remember that P, the dipole moment, is a vector, and electric field is a vector. And so this is scalar product right here. So the work that you do is actually the negative of the scalar product between P and E. And by the way, the work that you do, the work that some external force comes in and does to rotate this molecule against the electric field, that is stored potential energy. So there's our equation, that the work to rotate it from perpendicular to some angle alpha is negative PE times cosine alpha. Now what that means, if we try to plug in different values for that angle alpha, depending on what quadrant it goes to, well, work is going to be positive if the angle is anywhere between 90 degrees and 270 degrees. You look at my picture at the top, it's starting at 90. And the electric field has an inclination to rotate it clockwise. But we want to come in and rotate it counterclockwise. So we have to do work. We have to do positive work against the electric field. And so it's going to be positive. Now, what if alpha is less than 90 degrees, maybe just 40 degrees? And you can see by my second picture, that means rotating it clockwise. The thing is, the electric field is inclined to rotate it in that direction anyway. It doesn't need any extra help. So the work that you do is actually going to be negative. And if you plug in, just to test that mathematically, plug in some values such as alpha being 45 degrees, for example, or pi over 4 radians, and you'll see that you're going to get negative work. In general, the work required to rotate the electric dipole between two angles, so this is more generally, not just going from 90 degrees to some other angle, but just in general between two angles, is this. And here I'm redoing the work I did on the previous page, but I'm not assuming an initial angle. I'm just going from angle alpha to angle beta. So we take the integral from alpha to beta of PE sine theta d theta. That becomes negative PE of cosine theta taken between the two limits of integration. So it becomes negative PE of cosine beta minus cosine alpha. In the homework, problem number 60 involves using this formula and rotating a dipole from 30 degrees to anti-parallel with the electric field, which means 180 degrees. Let's do an example from the book. This is problem number 61. It says a molecule has its dipole moment aligned with a 1.2 kilonewton per coulomb electric field. If it takes 3.1 times 10 to the negative 27 joules to reverse the molecule's orientation, what is its dipole moment? All right, so you see the picture right here. It says it's aligned with the electric field. I've given the picture with the dipole a bit crooked with the electric field just so you can see the angle theta. So in this case, theta is going to start out as 0 degrees, the dipole pointing completely in the direction of the electric field. And then it's saying that we come in and do work to turn the dipole around 180 degrees, make it face the other direction. And so we're making theta, in this case, go from 0 to pi radians, or in degrees from 0 to 180 degrees. So we can say that work equals, and I've just started the derivation from the beginning, work is the integral taken from 0 to pi of tau delta theta, or d theta rather, is the integral 0 to pi of PE sine theta, because that's what tau or torque is. And taking that integration, we get negative PE times cosine theta taken from 0 to pi. So we plug in the limits of integration, 0 and pi. We get negative PE cosine pi. And you think, what is cosine pi? That is negative 1. Minus cosine of 0, which is 1. So the bit in the parentheses becomes negative 2. So negative PE times negative 2 becomes 2 PE. Work equals 2 times the dipole moment times the electric field. Now the question gives the work, and we have to figure out what is the dipole field, or what is the dipole moment. And so we solve it for P. And we get work over 2E, plug in those numbers, and we get 1.3 times 10 to the negative 30th coulomb meters. As I close this section in this chapter, I want to talk about an application of dipoles in an electric field. And in an earlier section, I mentioned that water is a dipole molecule. And I want to talk about microwave ovens and how they heat up our food. A water molecule, and that's what our food largely consists of, a whole lot of water molecules, is the way the atoms are arranged. It's got a positive side towards the end where the hydrogen atoms are, and a more negative side where the oxygen atoms or atom is. And so if you look at the diagram on the right, more simplified, it can be seen as a dipole, positive on one side, negative on the other side. A microwave oven produces electromagnetic waves. And later on the semester, we'll talk more about magnetism. That's the B field right there. But it's a continuously changing in a sine curve electric and magnetic field. Let's ignore for right now the magnetic field and focus on the electric field. You can see the way continuously the electric field is changing in its orientation. It goes up and down, and then up, and then down. So it's constantly changing which way it's facing. And so you can imagine if there's a polar molecule in this, such as water, that polar molecule is going to keep on trying to stay aligned with the electric field, and it's going to keep on rotating. Now, a microwave oven tends to be in the frequency along the gigahertz range, and so this is going to be a couple of billion times per second. So when we subject water molecules that are in the food to this ever-changing electric field, they keep being agitated. They keep realigning with the continuously changing, a couple of billion times per second, electric field, going one way and then the other. So in a microwave oven, the changing electric field rotates the polar water molecule into alignment with the field. So this adds kinetic energy to the molecules of the food, and also there's internal friction between the molecules, and overall it causes a heating up of the food. That is the end of section 25, Matter in Electric Fields, and that is also the end of chapter 20. Have a great day.